Hi students, today we are going to see about Coulomb's inverse square law of magnetism. Here this is same as electricity chapter. There the Coulomb's inverse square law is also used. Here it is something different. You consider two bar magnets A and B. You see this diagram. There are two magnets A and B. You see north pole and north pole, when they bring close to each other, repulsive force will take place, whereas north pole and south pole, they will attract each other. So this is a familiar fact, you know, opposite charges attract and like charges repel each other. This is a universal phenomena. Opposite charges will attract and like charges will repel each other. Based on this, we are going to see about Coulomb's inverse square law of magnetism. And this is the statement: the force of attraction or repulsion between two magnetic poles is directly proportional to product of their pole strengths and inversely proportional to the square of the distance between them. For that, you have this expression: F is directly proportional to QMA QMB divided by R square. QMA is pole strength of the first magnet, QMB is pole strength of the second magnet, and R is the distance between these two pole strengths. And the proportionality constant is removed by is equal to sign. So F vector is equal to K. This is the proportionality constant. This proportionality constant K is nothing but mu naught by 4 pi. Mu naught is permeability of free space, whose value is given by 10 power minus 7 Henry per meter. Here we are using mu naught, whereas in electricity we are using epsilon naught. So this is about Coulomb's inverse square law of magnetism, which you have studied in electricity chapter. There, instead of pole strengths, we are using charges, but here pole strength is taken. And based on this, we are going to derive magnetic field at a point along the axial line of the magnetic dipole. Here the magnetic dipole is nothing but a bar magnet. And here you see this diagram. Here this is the bar magnet, the south pole and north pole. We are going to find out the magnetic field at this point. And this is the axial line of the bar magnet. So here when you see, the total length of the bar magnet is 2L, and O is the center part of the bar magnet, and we are going to derive an expression for magnetic induction or magnetic field at this point C. Now when you see the distance between N and C, it is R minus L, and when you see the distance between S and C, it is R plus L. So these are the things you should know. R is the distance between O and C, and in this case the force due to north pole is acting in this direction, that is acting away, whereas the force due to south pole is acting towards this. So they will be in the opposite direction. And in this case you are having, let N be the north pole and S be the south pole of the bar magnet, each of the pole strength Qm and separated by a distance of 2L, that you already know. And the force experienced by unit north pole at C is due to the pole strength can be computed using Coulomb's law of magnetism. Now we are going to apply Coulomb's law, and according to Coulomb's law, Fn vector is equal to mu naught by 4 pi into Qm divided by R minus L the whole square into I cap. Here we are using R minus L because the distance between the north pole and C is R minus L. Similar expression is used for the force due to south pole, but here the distance is varying, so instead of R minus L you are using R plus L the whole square, and here this is minus I cap because the direction is opposite to that of Fn. So now the total force is F vector is equal to F1 vector plus Fs vector. So you have to add both of them. So F vector plus Fn vector, this is Fs vector, and this minus sign is taken here, and so this minus sign is here. You are taking mu naught Qm by 4 pi outside, 1 by R minus L the whole square minus 1 by R plus L the whole square, and you know R minus L into R plus L is equal to R square minus L square. This is mathematical equation. So here instead of this common denominator, you can substitute R square minus L square the whole square, and here this is 2R Qm, this is nothing but Pm, because Pm is dipole moment. The dipole moment is given by Qm into 2L. So substituting that, you will get P external is equal to mu naught by 4 pi 2r Pm divided by r square minus L square the whole square into I cap. And when you see a case where r is very greater than L, so that is length of the magnet is very negligible. You are taking a very small magnet. In such a case, you can leave this L square. So this will become r power 4. So the expression now becomes B external vector is equal to mu naught by 4 pi 2 Pm by r cube. Already we are having one r and r get cancelled. So here what is this Pm into I cap? This is nothing but Pm vector. Pm vector, you know, that is magnetic dipole moment. So the final equation is B external vector is equal to mu naught by 4 pi r cube into 2 Pm vector. This is the axial line equation. Next we are going to see about equatorial line equation. For that the diagram is different, and here you see this is the bar magnet, and here this is point C, which is on the equatorial line. Axial line means along in this direction, but equatorial means at C. At C, what is the force due to north pole? That is in this direction. And what is at magnetic force due to south pole? That is in this direction, Fs vector. So this is Fn vector, this is Fs vector. This is acting away from the magnet, this is acting towards the bar magnet. When you take the resultant of this two, this is given by r vector. So, and here you know this is 2L, so this length is L, and the distance of C from point O is r. And so taking this right angle, what is hypotenuse? Hypotenuse is given by r dash, which is given by r square plus x square the whole square, r square plus L square the whole square according to Pythagoras theorem. And so here what is force due to north pole? And so when you see this diagram, you can understand easily. This is force due to north pole, which is resolved into two components. This is Fn cos theta minus I cap, because this is acting in the minus direction. Here this is Fn sin theta j cap. So what is Fn vector now? Minus Fn cos theta I cap plus Fn sin theta j cap, and you already derived this. Fn is equal to mu naught by 4 pi into Qm divided by r dash square. This is the equation for Fn. Now when you take this Fs, again this Fs is resolved into two components. Here this is horizontal component, this is the vertical component. Here you change, this is minus Fs cos theta I cap. This is in negative x direction. So minus sign should be here, and this is Fs. You change this equation. And what about this component? This is Fs sin theta minus j cap, because this is in the negative y direction. So minus j cap. So what is Fs vector now? Fs vector is minus Fs cos theta I cap minus Fs sin theta j cap. Both are in negative direction. So both the terms will have negative sign. Already you know Fs is equal to mu naught by 4 pi Qm divided by r dash square. And here you have to add both of them. So F is equal to Fn plus Fs. So you have to add equation 315 and 316. So when you add this, sin theta and sin theta term will get cancelled. So you will get B vector is equal to minus of Fn plus Fs cos theta I cap. Sin theta terms get cancelled. And you know Fn is equal to Fs. So substituting for Fn and Fs, you will get a 2 mu, because 2 Fn. So 2 mu by 4 by Qm r dash square into cos theta I cap, because this is in the negative direction. And so here you substitute for now cos theta. And you know cos theta, you take this right angle triangle. In this, if this is theta, cos theta is given by adjacent by hypotenuse. So cos theta is equal to adjacent by hypotenuse. Adjacent is L, hypotenuse is r dash. and L by what is R dash? R square plus L square the whole power half. Substituting this, you will get a B equation, and here also Qm into 2L, this is replaced by Pm, where Pm is magnetic dipole moment. So the same equation is repeated here. And in this case also, R is very greater than L. In such a case, you can neglect this L square term, so this will become R power 4. So what happens to this equation? Already we are having R square 3 by 2. So R2 and 2 get cancelled, so you will get R cube. So what is B equatorial now? Mu naught by 4 pi Pm by R cube into I cap. And here Pm I cap can be written as Pm vector, because when you combine with the unit vector, you will get the vector quantity. So instead of Pm I cap, you substitute Pm vector. So here the magnitude of B axial is twice that of the magnitude of B equatorial, because when you compare axial line equation and equatorial line equation, in axial line equation we are having 2 here, but here the 2 is absent, which means the magnitude of B axial is greater than, that is 2 times greater than the magnitude of B equatorial. So this is about magnetic field along the equatorial line. Next we are going to see about torque acting on a bar magnet in uniform magnetic field. You know torque is nothing but rotating force. Torque is nothing but rotating force. So here you are having north pole and south pole. This is uniform magnetic field. Here you are having the magnet whose length is 2L. When this is kept in this uniform magnetic field, it will rotate in the clockwise direction. So this rotating force is nothing but torque. We are going to derive the expression for this torque. So here each pole experiences a force of magnitude QMB, but in opposite direction. So here there are QMP and QMB which is acting in opposite direction, and which will rotate and try to align in the direction of the magnetic field. And what is Fn vector? Qm into B vector. This is force experienced by north pole. Similarly, the force experienced by south pole, that is minus sign, because it will act in the opposite direction. When you add both these equations, you will get 0. So the net force is 0, but there will be torque. So the bar magnet will try to rotate in the clockwise direction in order to align with the field. So now tau vector is given by perpendicular distance into force, because you know torque is force into perpendicular distance. So here the perpendicular distance is nothing but ON. Here the distance between ON is L, and Fn vector you know QMB vector. This is the vector product plus OS vector into minus QMB, because here this is in the opposite direction. And so here the next, since we consider only the magnitude, you can leave this negative sign. So you will get tau is equal to L, because the distance of ON and OS is L, into QMB sin theta. When you add these two, you will get 2L QMB sin theta, and you know this 2L QM is nothing but PM. So tau is equal to PM B sin theta, and this is in vector product form. So in vector notation, you can write tau vector is equal to PM vector cross B vector, because this is in the form of vector product. So you are replacing vector product in this equation. So this is torque of bar magnet when it is placed in uniform magnetic field. Next we shall see about potential energy of the bar magnet in a uniform magnetic field. Here this is the uniform magnetic field and the magnet is placed here. We are going to see about what is the potential energy. This bar magnet makes an angle theta with the uniform magnetic field. And so here what is external force? First tau, you know tau B is equal to PM vector B vector sin theta. This equation you already know. This is a vector product equation. And when you see the external torque, we apply some external torque to rotate through an angle d theta. For that we do some work that is given by dW. You know W is equal to tau theta. This is a familiar equation, that is work done is equal to torque into angular displacement. This is you have studied in 11th standard. So dW, that is a very small work done, is given by tau external into d theta. So this tau external is nothing but tau b vector. So you can replace this tau external by tau. So what is dW now? You know, tau, instead of tau we can write PMB sin theta d theta. How can you find out W from this? First, initially you can take the angle is changing from theta dash to theta. So you have to apply the lower limit theta dash and the upper limit theta and tau d theta. And when you substitute this, you will get this expression. And what is integral sin theta d theta? Integral sin theta d theta is minus cos theta. D theta shouldn't come. So you have PMB into minus cos theta. The limits are from theta dash to theta. Theta is the initial angle and theta dash is the initial angle and theta is the final angle, because the bar magnet is rotated from an angular position theta dash to the angular position theta. And so here, substituting the upper limit and the lower limit, this is upper limit minus lower limit. Suppose if you take that the initial position is 90 degree, at an angle of 90 degree, this term will become 0. So you will get u is equal to minus PMB cos theta. Why you are taking u here? Because you know the work done is stored as potential energy. So instead of W, you can substitute u, because the work done is nothing but potential energy. Now this is in scalar product form. So u is equal to minus Pm vector dot B vector. So this is the final equation for the potential energy. And here you can take two cases, case 1 and case 2. In first case, the angle theta is equal to 0. When you substitute 0 here, cos 0 is 1. So you will get u is equal to minus PMB. This is minimum value because this is negative. Suppose if you substitute theta is equal to 180 degree, then cos 180 is minus 1. So this will become PMB. This is the maximum value. From this you can say that the potential energy of the bar magnet is minimum when it is aligned along with the external magnetic field, and the maximum when the bar magnet is aligned anti-parallel to the field. So theta is equal to 0 means it is aligned with the field. Theta is equal to 180 degree means it is anti-parallel to the field. So we have derived an expression for the potential energy. So far we have seen about Coulomb's inverse square law, axial line equation, equatorial line equation, then torque and potential energy. Hope you understand, girls.